Now, the stuff I'll talk about today, a lot of it applies to serverless platforms in general, but I've mostly worked with AWS. So when I give you some more concrete data, that's limited to AWS. And I'd like to kind of give you some of my experiences related to running in this new, wonderful new way of developing applications and deploying applications. Somewhere in 2016, a product I'm working on, we decided to start using AWS Lambda, and by the end of 2016, we've moved all our services onto Lambda. And we've been kind of running serverless for about 2.5 or 3 years in that. So there's some nice emerging patterns there. I think it's too early as a community still to talk about best practices because we've not even seen where this is going. But there's some emerging practices that are interesting, some constraints that were not really that known to me or logical to me when we started, and that's what I'd like to talk about. So in terms of serverless, it's a horrible buzzword, and people have been talking about how there's still servers there and stuff like that. But what's interesting for me is really how that starts changing the possibilities of deploying applications. And a lot of the stuff, once you take the server out of the picture, the write-up of the server, a lot of the stuff that I at least thought were good practices or even best practices designing distributed systems slightly change. And I've realized those things are not really best practices, they were just solutions for certain constraints. Once you remove those constraints, some other solutions start applying. And that's kind of what I'd like to talk about today. Now, in terms of serverless, the right server to think about is the socket server. Not the machine, not kind of database and stuff like that, but really the socket server, because serverless platforms give the responsibility for listening and responding to network sockets to the operator, to AWS, to Google, to Microsoft. Your application is no longer in control of the socket. That's the server we're talking about. And I like to think about this kind of, this is serverless the same way that Wi-Fi is wireless. Like, you all know that if you are kind of using your mobile phone here and it's connected to the internet, there is a router somewhere in this room. And there's an Ethernet cable even here. It's not connected to anything, but there is a router, there are cables, but you don't have to actively think about or manage those cables. That's kind of where this is going. Now, in terms of the application and applications and stuff like that is interesting to change. This was my life for the last, 20 years. There's a client device, it's talking to some load balancer in a highly distributed scenario. This is talking to machines that are running application servers, whether it's JBoss or is it Ruby on Rails or is it a PHP thing or something like web servers, application servers. These things are talking to databases, storage, and things like that. I assume everybody in this room has built something like this. Now, what's really interesting is to show people that have spent years and years and years of building something like this an option to potentially do this. And this is where people start running away. It's like, oh, this is insecure. Like allowing a client device directly to write into our database, or allowing a web browser to directly talk to the backend storage. And that's kind of part of what makes serverless so puzzling, because this is actually something that I assume most people in this room will be doing, if not now, then 5 years from now. Economically, nothing else is going to make sense. And that's kind of part of what I meant by stuff we thought were best practices, where, of course, you put a server in the middle or an application server in the middle to secure and validate and coordinate and everything. That is not necessarily where we need to go. So in terms of kind of 5 things, the 5 things that we need to start thinking about really socketless development, not serverless development, are constraints around pricing. And for me, personally, this was one of the biggest things to get over in the head. I think, this is a technical conference. Everybody here, I assume, works in technology. For us, it's interesting to look at these things from a technical perspective. AWS Lambda, Google Cloud Functions, Azure Functions, they are technically really complicated to pull off. They're kind of supercharged containers. They work amazing. Technically, it's a complicated thing, but it's just an evolutionary step on app virtualization that started maybe 10, 15 years ago. What's really revolutionary, not evolutionary, is the pricing. And this is what opens up lots of really interesting possibilities. Pricing then starts affecting how we can manage versions, how tasks get routed, how we manage state, and what we and how we secure the application. So that's kind of what I'm going to talk about very briefly and give you some of my kind of findings and conclusions on that. So in terms of pricing, the revolutionary thing here is that cloud providers got to the scale where they can offer pricing for utilization, actual utilization rather than reserved capacity. Ever since immortal mainframes, people were concerned about reserving capacity. We were concerned about providing failover capacity. We were concerned about providing backups. We were concerned about providing an environment that is reserved, or at least can be utilized and ramped up quickly if the need comes and things like that. I remember I used to work with a big bookmaker in England where I think they do about 60% of their yearly revenue in about 3 hours before a really big horse race on one particular Saturday. So for months before that Saturday, it's chaos. People are preparing a new version of the application that's completely static. They're taking out security measures from card processing. There's lots and lots of stuff to prepare for that thing because they only have a certain amount of capacity in the data center. They cannot get more. Now, with virtual machines and things like that, things became better, but it's still, we need to think and plan and reserve capacity. What Lambda has done, what Google Cloud Functions have done, is you effectively pay for what you use. It's like electricity. Oh, you need more now, that's fine. You don't need it now, that's fine as well. And they are taking the risk of coordinating and all this stuff. So the way this thing works in AWS is just illustrative. If I take a virtual machine in US East 1 with 512 megabytes of memory, you cannot actually reserve it like that, but what AWS will charge you for is 0 point something per request and something for every 100 milliseconds in the CPU. Not the number of users, not the number of machines, not the number of environments, number of requests. What that means is that it costs exactly the same amount of money to have an environment just for this Saturday, and 3 different environments and 5 different environments is the number of requests that matter, not the number of machines or number of processors. What that means is that you don't have to worry about anymore about reserving capacity, planning up, figuring out how to do failovers and things like that. So zeros are really difficult to multiply on a monthly level. This is what it comes down to. Again, illustratively, it's difficult to compare EC2 instances or containers to Lambdas because they charge different things. But if we have a task, say something important that runs every 5 minutes for 100 milliseconds, this is payments on a reasonably sized website, the cost would come to about $1 a month. If you have a Lambda that's working with 512 megabytes and it's like non-stop working for a month, that would come to about $27. So that's how these numbers multiply. Now, it's difficult really to compare that to reserved instances because they charge different things, but a EC2 equivalent and a failover would cost about $9 a month. So we're talking about the difference in cost that's from several magnitudes, 2 magnitudes less or 3 magnitudes less, to about 3 times more. And this is where a lot of the stuff gets flame wars and things like that on the internet. People say, oh, it's cheaper this way or it's cheaper that way. One of the really interesting things, if we start not managing the socket anymore, if the provider manages the socket, is a lot of the operational stuff goes away with that as well. So in this $27 or in this in this 1 cent, most of ops is included. In fact, Simon Wardley has this famous talk where he talked about how if your organization has not done DevOps yet, don't bother. Just go serverless and skip a whole generation of upgrades. Because DevOps is just included in the price. And that's why this 27 or 9 doesn't really make a difference. So stuff like monitoring, scaling, failovers, backups, blue-green deployments, all of that is actually built in. Because that is the responsibility of whoever's managing the socket. And that's what I think is revolutionary here. The product I'm building, there's only 2 of us. We do marketing, we do sales, we do blog posts, we do development, we do support, we do testing, we do everything. And it's really, really important for me to spend time doing what makes sense rather than stuff that I really shouldn't be doing. And where the penny really dropped was kind of August last year. There were these problems with Intel processors where people were discovering ways to break them. We got an email from an IT admin of a concerned customer saying, oh, you know, this new vulnerability was published. We need to know what you plan to do about it. And, you know, we don't want people to steal our data. I just woke up. I saw that email. I typed the CV number into Google. The first response was AWS Lambda was already patched. That's exactly what I want to see. So kind of, you know, although this can be 3 times more expensive than EC2, when you count the whole time you need to spend on it, it's actually a lot cheaper. So with the socket, they take the responsibility for scaling, capacity planning, and all the other stuff. And that's what's kind of revolutionary about it. Because then we can start looking at how does that affect the rest of the application. So, for example, one of the things that is really interesting to look at is what do we do with messages that, you know, if you start scaling and it explodes, we lose them. And what Amazon started offering just as a configuration property last year or kind of a year ago was these things called dead letter queues. So if you have this kind of highly scalable thing that, you know, goes up and down, sometimes dies, sometimes doesn't die, and you miss a message, what Amazon is going to do, first of all, if there's an exception in your function, the first assumption they make is that there's something wrong with that Lambda instance. You know, the instances died, there's a problem with hardware, something like that. So what they're going to do, they're going to shut that one down, they're going to send it automatically to a new instance. If there's an exception there, the second assumption they make is there's something wrong with the AWS infrastructure that this thing is using. Maybe S3 is too busy, maybe the database is too busy. And then what they're going to do is 2 seconds later, they're going to send that message again. And then if there's a third exception for the same message, they're going to say, well, the problem is in your code. All of this is done automatically. You don't have to program it. With kind of any kind of load balancers, with any, you know, server-side environments, it's the ops job or developer's job to program this stuff. You get this included in the price, and even if that fails third time, you can just say, well, send me this message so I can log it, debug it somewhere else. You can use this thing called the dead letter queue. If there's 3 exceptions for the same message, it goes somewhere. This can go to a queue, a message topic, or ironically can invoke a different Lambda function. Or not ironically, kind of curiously can invoke another Lambda function. So you can have this thing saying, oh, you know, we're going to process this thing using the fast mechanism, and if for some reason it explodes 3 times, go and send it to the overnight job. It's included in the price. Another thing that's kind of included in the price operationally is all this stuff around deploying and managing different deployments. So one of the things I really liked about this is you can do gradual deployments because the number of requests is important, not the number of environments. When you deploy a new function, you can just say, well, the deployment type is canary 10% over 10 minutes. And that means when I deploy a new version of my application, give the new version only 10% of the traffic. If there's nothing wrong, at the end of the 10 minutes, give the new version the rest of the traffic. Now, nothing wrong depends on you. Nothing wrong might be measuring exceptions, or it might be measuring a difference in user conversion, or it might be measuring the difference in sales. So it's trivial easy to set up something that, you know, if you deploy a new version and people are not buying as much with that version as before, there's something wrong. Go and roll it back. Now, stuff like this was available to companies that were Facebook and Google size 5 years ago. Now a team of 2 people can do this stuff, and it's included in the price. And that's why I think, you know, this whole comparison with instances of virtual machines is a bit unfair. So in terms of that, what's interesting about this is not only is this included in the price, but it doesn't cost any more than doing a normal deployment. And, you know, you can start running this thing and it says, oh, I'm giving it 90%. They actually have a couple of different models here. One model is to do it step by step. So every 5 minutes, every minute, every 10 minutes, your new version gets more traffic. The other one is to do this kind of 2-step thing where you say, give me 5% or give me 1% now and then give me the rest later. And you effectively have 2 versions of your application running at the same time. because it's priced per request, not priced per version, it costs exactly the same as having a single version. Now think about this. Every time you've done a big server deployment in the past, usually there's only one production environment. Even with kind of reserved virtual machines and things like that, there's only one production environment because creating another production environment costs double as much. That's why testing environments, staging environments are usually slimmed down versions of the real thing. And then, the production environment is not really I/O bound because it has this monster storage there, but the staging environment has much cheaper storage and it's not CPU bound, it's I/O bound, and people don't kind of test performance there and things like that. With pricing based on request, it doesn't cost any more to set up 2 environments, 3 environments, 5 environments, 10 environments. So kind of the really important effect of this is the versions and environments have no effect on price. And this was a major constraint of application development for the last 50 years. It's gone. And with that constraint, lots of the stuff that was the best practice, like blue-green deployments, well, is it still a good practice or not? So kind of, there's a couple of interesting consequences of that. First of all, what we do now is we really look at different pricing needs when we think about splitting stuff into functions. For example, for this app that I'm building now, we have lots of format converters. People upload documents, we convert it into other formats. We have an SVG converter and a PDF converter. They share 99.9% of the code. In fact, the PDF converter first produces an SVG and then runs RSVG to convert it into PDF. Now, although they share 99% to 99.999% of the code, they have different CPU and memory requirements because the SVG converter is just working with text streams. It needs no, like 128 megabytes of memory. RSVG is a memory hog. The external utility we run is a memory hog. It needs a lot of memory. It needs a processor. What would be logical earlier is to keep these two things in the same service, in the same module, so we don't have to kind of pay for multiple environments. Doing the same thing with Lambda actually costs more money, because splitting into 2 different things allows us to pay for a higher memory watermark for PDF and not pay for the higher memory watermark for SVG. They have different needs. So another thing that's kind of really interesting is, just make new environments for testing every time you need them. Where people previously had one testing environment and then you have developers and testers fighting about it, or somebody is doing some kind of testing on that and they poison the data and then your test fails, just kind of make a new environment completely. Have a production for every developer. Complete copy of it, because it costs exactly the same. It's based on the number of requests, it's based on actual usage, rather than the number of machines, services, or anything like that. Another interesting thing here that opens up is, well, if you need to have some kind of experimental version, you want to try out an idea and do A/B testing. Previously, kind of, people used A/B testing only on the front end because that's easy to do. Now you can do A/B testing back-to-back, complete stack. So another thing that's kind of really interesting here as an option is just keep all versions around. Just, don't remove old versions. They can be there. We had a problem with PayPal. PayPal decided for some reason, after we changed our endpoint URL, to keep sending us all the messages for previous subscriptions before we changed the URL to the old URL. Now, we just decided let's keep the old version there, and that's fine. At some point, people with these old subscriptions are going to upgrade or die or something like that. We can keep the application there as long as people are using it. That's okay, perfectly fine. So, kind of the next thing that this thing starts impacting is what connects to what. And this is where Lambda is kind of interestingly specific. So every time you deploy a new version of a function, you can say, look, this version is important. You don't have to, but you can say this version is important. I want to keep it around. That's called publishing a version. And when you publish a version, Lambda numerically increases published versions. So, 1, 2, 3, and things like that. And then forever, you can call an older version as long as you don't delete it. And you can set up the clients to call that particular version. You can keep PayPal calling an older version of it. Now, because kind of numerical versions are not trivial to track, In the concept of Lambda, there's also something called an alias. An alias is a textual pointer to a numerical version. And you can also set up event sources to call an alias. So if I set up an API to call live or to call old PayPal or something like that, then I can kind of deploy a function, call it testing, properly kind of evaluate it in testing, and then when it's done testing, I can just say, look, live is now whatever testing was. All the events for live are now going to the testing thing as well. So this is not necessarily one-to-one. You can have an alias pointing at multiple versions. That's how they do gradual deployments. And you can say 90% of live is going to version 1, 10% of live is going to version 2. And you can have multiple aliases, such as testing and live, pointing to the same numerical thing. So kind of is many to many, but what's interesting about this is, at the moment, it's kind of trivial easy to declare that by just putting, if you're using CloudFormation and Sam just put auto-publish alias live there, whenever this function gets updated, live gets reassigned to that when it's done. So the trick here is, although CloudFormation provides some kind of resemblance of an atomic deployment, it is atomic in a sense that if you have multiple functions, multiple resources in the same application, it will either succeed or roll back everything, but during deployment, these functions will get updated at different times. If I have 3 functions here, one function is going to get updated, and another function gets updated, and a third function gets updated. So for a brief period of time, you will have potentially incompatible versions of different functions running. Now, unlike uploading a single package to something, it's really not possible to guarantee that these things are completely consistent. If you go to your cloud function stack anywhere, you can just see these things when you go to the qualifiers tab, and you can see here I have 2 versions. The first one is assigned to alias. But if you go to this thing during deployment, you will actually see that these things are getting updated at different times. And the key thing to remember here that's kind of a bit puzzling when you start working with this is there's no way to guarantee updating 2 resources at exactly the same time. That's the part of kind of design that still remains with application developers. So there's a couple of consequences for that. First of all, reassigning an alias is much faster than uploading a package. So use aliases for everything. To kind of don't wire event sources to the latest version because it's not really a known state what the latest version is during deployment. Use aliases. It's trivial easy to do that. Another thing kind of we've learned is if you really need to process some data consistently, send it as a whole thing to a function as an event. Don't make it chatty, make it an aggregate so that you're not into this situation where I'm sending a username, then I'm sending a kind of login request, then I'm sending kind of some other data, and it might hit 2 different versions of the same function throughout the deployment. Send data aggregates. With this thing, one of the things we burnt our fingers quite a few times and then kind of learned how to fight against that is if you need to be sure kind of what format is compatible with what version of your function, write the format version into the aggregate when you're saving it. Or write the format version in an event when you're sending it to the function. So then a function can say, look, I received an event format version 4. I'm actually good for format version 5, so I need to upgrade this stuff. Because during a deployment, some of the services were switched, some were not. And as another consequence, the code that absolutely must be consistent within the same millisecond, put it into the same function. There's lots of stuff where people are talking about, is it a monolith, is it a microservice, is it a nanoservice, what is a function? Kind of, I think, divide code that has different memory, CPU needs into different things, but bundle code that really has to be consistent into the same function, that's kind of our guidelines so far for this. So kind of the next thing that is interesting here, because we don't control the socket anymore as application developers, is how the tasks get routed. Yes, I say this goes to live, but what is live? And what Lambda does, this is probably different for other systems, I can't talk about that. What Lambda does is Lambda actually does not spin a container for a new version of a function until the first event asking for that version comes in. So you can deploy something called live, but the old one can still be running if the events are going for that thing. the new one is still not running. The first time an event comes in asking for version 5, Lambda spins up a new container for version 5. So it doesn't actually shut down or start containers when you deploy. It just creates a new version available for anybody who wants to look at it. And Lambda decides how many instances it's going to run. You cannot tell Lambda, look, keep 5 instances for me because I'm going to have a lot of traffic on Saturday. Amazon does their own algorithms for this. You as an application developer have no control over it, which means there's no sticky sessions. With an application load balancer, with a kind of service, usually there's some kind of routing there that says, oh, send all the requests from this user to the same machine. So it can keep some in-memory state or do something. That's not possible with Lambda. And a big problem with that is lots of people take their existing website code that has some in-memory state, they deploy it to this, and then you test it, there's not enough traffic to start 2 instances and everything works okay. You deploy to production and all of a sudden, the requests for the same user are going to different places. So there's no such thing as a sticky session here. There's some cheats about this, I'll show you about this later. And the only guarantee that Amazon provides so far is availability. The current SLA for Lambda is 99.95, which means that if something is not available 99.95% of the time, Amazon will start giving you your money back. Usually, this is not an issue because everything is asynchronous anyway, so we've not really had trouble with this since we started. But there is no latency or processing time SLA. There's nothing that guarantees that a message is going to be processed in a second, 2 seconds, 5 milliseconds, anything like that. And I said, in case of errors, you'll get retries. First one immediately, second one after a few seconds, then a third one after, I think, 20 seconds or something like that. So the whole platform at the moment is really optimized for throughput, not for low latency or not for time to process. We, when moving from an application hosting platform to Lambda, put some metrics in the browsers to see user latencies in the browser. There was no big difference between Heroku and Lambda. Your experience might vary, but there's a couple of other limits. The one limit that's hard at the moment is you can only take up to 15 minutes in the processor per task. You cannot do anything longer than 15 minutes, and you can't ask for more. Some people cheat by splitting tasks differently, or if you don't finish, saving state and then restarting another one. But designing an app around this again is slightly slightly difficult. There are alternative services like Fargate that are built similarly, but you give them a Docker container, it runs for a long time. For example, I have this video editing application that I'm building now, and because people can upload massive files to convert, I can't guarantee this is going to finish in 15 minutes, so I'll spin it off and send it elsewhere. This thing starts significantly slower than Lambda, but if the task is 15 minutes or more, then maybe that's okay. And there's about maximum 1,000 concurrent instances for all your functions in a single account that can run at the same time. You can ask for more. If you really go to something that requires a lot more, people got stung with this, so ask for more before it gets hurting. So there's a couple of consequences of that. So the first consequence of that on Lambda in particular is startup times and reusing and things like that. So in 2005, there were lots of posts around what's called a cold start. A cold start is where Lambda needs to create a new instance to receive your requests, and people are talking about how this is taking too long. You need to fight against this. You need to keep your Lambdas warm and things like that. My experimental data, Amazon doesn't really publish any official data about this, is that for a new instance, a new version of the function, or when the existing instances can't cope with capacity, if you're doing stuff in Python or JavaScript, it's less than 1 second. If you're doing stuff in Java, it's a couple of seconds. And if you attach it to a virtual private network, virtual private cloud, it's more than 10 seconds, so that's useless for that. So there's a couple of interesting aspects of this as well. There's no official data on how frequently an instance is going to get reused, but my experience is that if a new message comes in within a few minutes, it will be reused if it's not busy. If it's more than 10 minutes, you're probably going to get a new instance. And reaching an existing instance from event sources is about kind of 50 to 100 milliseconds. So for a normal web user, they're not going to notice something like this because network latencies are just kind of like that, which means that the platform as it is now is great for any kind of HTTP API handling, webhooks, payment processing, things like that. It's great for tasks where a couple of 100 milliseconds is not so problematic. File conversions, reporting, and things like that. And anything that is really throughput bound, not latency bound, this is okay. Now, as a platform, it's been changing quite a lot. I wrote a book on this recently, and I was finished with the book, and then Amazon released a new version of this, and I had to rewrite 4 chapters before publishing the book. So it's very, very possibly that in a year's time or 2 years' time, there's going to be different constraints. But what I wouldn't use this for now is any kind of real-time or low-latency processing. If you have something where you absolutely need to guarantee that messages are handled within any reasonable time, don't do this. Any kind of continuous processing where you connect to a socket and then you feed stuff from Twitter or stuff like this is not good for that. Again, there are other services on Amazon that can be used for this. And because there's no real choice between types of CPUs at the moment on Lambda, I don't know about other services, things that depend on GPUs, like video rendering, no. So one of the kind of questions that people often start talking about when looking at routing and things like this, how do we know that somebody's not going to abuse this stuff? How do I protect against my competition just kind of spamming me or somebody kind of causing this thing to spin out of control? So there's a couple of ways this can be done, and again, ops is included in the price. So one thing that you can do for every function is you don't have to give it the whole 1,000 available things. You can give it 10, or you can give it 1 and create a nice little monolith. There is, if you're doing something that cannot be done in parallel, you can say 1, and Lambda will never start more than 1 instance of this. You still get all the failover, error recovery, and things like that, so there is a reason why you would want to do that. The other thing is, if you put an API gateway in front of it or something like that, you can actually put throttling limits on that. You can put even different throttling limits on different account types. So you can give your premium accounts some limit. You can give your kind of free accounts some other limit. So there's lots and lots of ways how to do this configuration-based. It's not such a big risk. And another thing I said, there's no routing control really, but you can cheat a bit. One thing that you can do is you can control parallelization with Kinesis. Kinesis is an additional service on Amazon, and Kinesis is a stream processor that works with shards. Shards are kind of sequences of events that are separated, and you give it a data field that it hashes to decide what shard to send something to. When you connect Kinesis to Lambdas, it guarantees that for a single shard, it's never going to have more than 1 function running on it, more than 1 instance running on it. So for example, for this collaboration tool we're building, we allow multiple users to write into the same file at the same time, but we use the file ID to select the shard. So that means that regardless of how many users are pumping data at the same time, no more than 1 Lambda instance is ever going to process a single file. So you don't have to lock, you don't have to kind of do these things. So that's a very useful pattern to kind of not have a single instance if you can't avoid parallelization, but to say, look, by user, by file, by account, by something, we're going to parallelize this stuff so you can still have 100 Lambdas running or 50 Lambdas running, but avoid all the distributed locking problems. So that's a very useful trick. Now, another thing that kind of confuses people a lot is state, because kind of for whatever, good or bad reason, they decided to call these things functions. I think one of the reasons was to avoid comparing it with containers and services and things like that, but functions, and especially Lambda, has meaning in functional programming. Lambda calculus is a branch of mathematics that deals with kind of computability and things like that, and people talk about functions and Lambdas. This brought a whole baggage of assumptions around it, and there's lots and lots of misguided posts that talk about how Lambdas are stateless. They're not. A Lambda instance will be reused within a few minutes, which means that there is an in-memory state there. A Lambda instance also has a 500 megabyte temp storage. where you can save stuff to reuse, to cache, and things like that. Now, for some some usages, this is a good thing. For some usages, this is a horribly bad thing. I mentioned that there's no control over how many instances run in a period of time. And even in this thing, Lambda might decide to kill this instance and start another one. So assuming that the state is preserved is wrong. But can you cache it for some things? Absolutely yes. If you need to download some external stuff to process, if you need to access something, you can use the temp space, you can use the in-memory thing, but don't do it for user-related stuff. Do it for application-related things that don't depend on a particular user. So don't keep user data in Lambda functions. That's a horribly bad idea. Put data somewhere else. There's S3, that's kind of an object store. There's DynamoDB, that's a data store. Relational databases are a big problem at the moment because relational databases typically require a VPC and then takes 10 seconds to start up a VPC. So if you need to use a relational database, what I suggest is have one Lambda function that receives requests and just chucks it on a queue very quickly, like Kinesis or something like that. Then have another one waking up after Kinesis on a VPC or something like that. That would allow you to reuse and avoid this kind of startup time. AppSync is another interesting platform for this that Amazon is offering. It's a hosted GraphQL endpoint that you can use to talk from the clients directly, the picture that I showed earlier on. And it's kind of consuming data. It has conflict resolution. It has offline support. Keep user data there. And again, you can set up Lambdas to read and write from that. So one of the things that kind of is also interesting when we start looking at where the data is and calls and stuff like that is security, because for every single request, Amazon needs to separately authorize it. There's no persistent connections. You don't own the socket, Amazon owns the socket. So for every single connection, IAM, that's kind of the Identity and Authentication Management Service, has to authorize the request, be it kind of from a client to Lambda or from Lambda to other resources. Which means that if your Lambda is saving or reading to databases or to a file system or something like that, every single request that goes out from that Lambda is separately authorized. Which means that kind of if a client device talks to the database or a Lambda talks to the database, it doesn't matter. It still has to be authorized. With normal server-side apps, you have this gateway in the middle. There's a application server. Requests hitting the application server are not trusted. Application server to database is trusted. In this case, it's not. And actually, there's no such thing as a background resource here, really, because S3 is available on using HTTPS. Dynamo is available using HTTPS. AppSync is available using HTTPS. So people can talk to you directly if IAM allows that. So that begs an interesting question. If you kind of look at a structure where the client sends some data to the API gateway sends it to Lambda, and Lambda saves it to the bucket. What is this thing actually doing? Is it doing something that's business important, or is it just there as a bouncer? Is it there just so kind of because we are in our minds thinking about, well, I need to send this data to my application writes to storage? Because there's several ways you can authorize a client to talk directly to S3. For example, for this app that we are building, we allow anonymous users to save files up to 100 kilobytes without even registering. So instead of this thing going through a Lambda and Lambda saying, is this 100 kilobytes or not, I can generate a pre-signed authorization to says, allow him to save files with this extension, with this prefix up to 100 kilobytes for the next 10 minutes. So the client can go and talk to this thing directly. So you can generate these signatures from a Lambda and then kind of go and get clients to talk directly to your backend storage. With Dynamo, you can say, allow a user to modify only the email property of their own record. Allow a user to read the user ID property from their record, but not to modify it. Allow everybody to read the total scoreboard, but only this backend process to write it, and things like that. And by doing these very, very micro resolutions that they had to do to support request-based pricing and request-based authorizations, you can benefit from that. For example, say somebody wants to upload a couple of gigabytes. We can send it to an application server through an API and then get stuck on multiple places. Or we can use a very quick Lambda signature to say, look, allow this person to upload 5 megabytes, and then go directly to S3, or go directly to Dynamo, or go somewhere else. There's a service called Cognito as well that allows people to do templated policies, which means I can say, users can go and write their own database records. Users can read the scoreboard or things like that. So instead of, if the only thing that kind of this thing in the middle is doing is a gatekeeper, just kind of move it out. It's going to be a lot faster because you don't have to pay for intermediaries. It's going to be a lot cheaper because it's going to be a lot more reliable. There's fewer components to change. And this is one of these kind of really wonderful things when you start thinking about request-based security and request-based pricing. The other thing is, we usually kind of, or at least I used to use the middleman for workflows and coordination. Oh, you want to convert a file? Good. You send it to the application server. The application server saves it to the storage, then calls the converter, then kind of polls the converter securely, and then exposes some kind of status to the user. Why? We can get platform events to fire off as well. Lambda is a universal glue on AWS, so almost anything can cause a Lambda function to start. You can do it by sending an email, you can do it by saving a file, you can do it by lots of different things. So you can configure S3 to say, whenever a file is uploaded to this prefix, or whenever a file is uploaded with this extension, call this Lambda function. So what that means is that if if the only thing that this thing in the middle is doing is orchestration, just don't worry about that. Use platform events. This is kind of how our conversion pipeline works. We have something that signs the uploads. We have, then the user can go and upload a large file directly to a bucket. When a file is uploaded to a bucket, the converter automatically starts. It saves it to the results bucket. And we have this other thing that kind of just gives people hey, this is where you go and look for the results. So the most expensive piece here is the API gateway. The second most expensive piece is Lambda. The third most expensive piece is S3. Which means that if you have, hey, is my file done? Going through an API gateway and Lambda and S3, you're paying probably 10 times as much than if you just tell them, oh, go to S3 and try getting the first 10 bytes of this and you'll see if it's done or not. Or go and ask for metadata. So don't use kind of this middle thing for orchestration. Well, another thing that kind of really opens up interestingly is once these things start, once we have these micro-level authorizations, and we can get client to talk to the backend resources, we can move orchestration for client workflows to the client device. Which means that all of a sudden your app is not just running on, 50, 60, 100 processors in Amazon, it's running on several hundreds of thousands of processors on clients' devices that you're not paying for. Move the workflow to the client device. So as a conclusion, thinking about removing the gatekeeper, that's kind of really serverless part of serverless. Remove the gatekeepers. Allows us to create applications that are faster because the client can talk to the storage directly. The client can very often use storage APIs that are much better. S3 has full support for partial uploads, for multi-part uploads and things like that. You don't have to build it, just kind of let the user use it. It allows us to do stuff that's cheaper because in a case of, hey, is my file done, is my file done, is my file done, by letting people talk directly to storage, you're going to save an order of magnitude more money by letting the client talk there directly. And it's also a lot more robust because we are removing stuff that can go wrong. Fewer components, kind of, it's more robust. So that's pretty much it. As I mentioned, I kind of wrote a book about this. It's out yesterday, and it's called Running Serverless. There's a lot more information about this, and you have a lot more code examples. If you go to this URL over the next 24 hours, you get 50% off the book. Thank you very much.